Okay, I'm going to show you a nice application of double integration in terms of polar coordinates with respect to the standard normal distribution. Okay, the standard normal distribution is also known as the Gaussian distribution. The standard normal distribution has the following a probability density function, 1 over the square root of 2 pi e to the minus 1/2 x squared. If you actually graph that probability density function, you get this bell-shaped curve. Okay, this bell-shaped curve. It turns out that the mean of that bell-shaped curve is 0 and its standard deviation is 1. If you don't know what these parameters mean here, that's okay. The mean should be easy for you to find. But that's okay. You've all seen this, the normal distribution, right? A standard one has these particular parameters. The mean is 0. The standard deviation is 1. Okay? Now, this is terminology from probability statistics. If a random variable cap x is distributed normally with parameters 0 and 1, mean 0, standard deviation 1, standard normal then, the probability that that random variable falls between these two values a and b is the integral from a to b of the probability density function. Okay, this is the standard idea for continuous distributions in probability. Okay, now, what's the probability that a random variable distributed this way is going to be between minus infinity and positive infinity? The answer is the probability is going to be 1, which we're going to associate with certainty, right? It's certain that the number lies somewhere between negative infinity and positive infinity. Okay, that would imply that 1 is the integral from minus infinity to positive infinity, 1 over the square root of 2 pi e to the minus 1/2 x squared dx. Okay, at least if this is a probability density function. By the way, to be a probability density function, this would have to hold together with this would always have to be greater than or equal to 0, the probability density function. That would be a definition of a probability density function. Anyway, now, if this is equal to 1, then what you can show pretty simply is the following. This implies this. Well, you see, I'm integrating from minus to infinity, this even probability density function, right? This has y-axis symmetry or vertical symmetry here. So that means if I integrate just from what? 0 to infinity, I should have what? Half of the square root of 2 pi, which is better written this way. So somehow, how can we show that this actually holds? How can we show that the integral from 0 to infinity of e to the minus 1/2 x squared dx is actually the square root of pi over 2? That seems strange. I wonder how we can do that. You guys remember something like this, e to the minus 1/2 x squared dx? That's a transcendental integral. You're not going to find a closed form expression for an antiderivative of that particular function. Okay, well, I'm going to show you how we can actually prove this using some techniques from Calculus 3 here. Okay, now I'm going to start out like this. I'm going to go the integral from 0 to infinity, e to the minus 1/2 x squared dx is equal to I. I'll give it a name. And I'm going to point out that this is the integral from 0 to infinity, e to the minus 1/2 y squared dy. Make good sense? Yeah, I just used a different variable over here, didn't I? Okay? Okay, well, if this is I, then this is also I, right? Okay? All right, we're going to think of these in terms of the x and y axis here, though. We're going to see this is not trivial here. Now, if I multiply these two integrals together, remember, I'm trying to find I somehow. I squared would be the product of these two integrals. So I'm going to go like this. The integral from 0 to infinity, e to the minus 1/2 x squared dx times the integral from 0 to infinity, e to the minus 1/2 y squared dy. Now, these are independent variables here. Do you notice I could actually do this because of our notions of iterated integrals and partial integration? I could actually be doing this here. Doesn't really matter what order I do this in. Okay. Right? I could think of what? Evaluating that inner integral. That gives me I, which I could bring out front, and then I'm evaluating the other integral, which is also I. So I get I squared, right? All right, let's actually write this in a regular way. Okay, everybody? All right. That means I squared is actually this double integral, 0 to infinity, 0 to infinity, e to the minus 1/2. Oh, wait a minute, these have a common base. If I multiply these together, I can actually add the exponents, and you see what I would get here. dx, dy, or dy, dx, doesn't matter. I'll just call it dA, okay? All right. Well, what am I really integrating over? I'm really integrating over, like I said, if I think of x and y in terms of the x and y axis, I'm integrating over the first quadrant, right? I'm integrating over the first quadrant. Okay. First quad, or Q1 or something. Now, do you see that x squared plus y squared there? That reminds me of polar coordinates. It's r squared. Now, what were differential changes in area in terms of polar coordinates? r dr d theta. r dr d theta over the first quadrant. Let's see, if I'm integrating over the first quadrant, okay, where would r be going from and to? It would be going from 0 to infinity, but theta would only be going from 0 to what? Pi over 2 to give me the first quadrant. E to the minus 1/2 r squared r dr d theta. Okay. Let's do this inner integral here. Integral from 0 to infinity, e to the minus 1/2 r squared r dr. Let's have u be negative 1/2 r squared. That would mean du is negative r dr. Perfect. Okay. So we actually have here, okay, e to the u. r dr would actually be what? Negative du. Okay. Let's see, r is going from 0 to infinity, so that means u is going from what? 0 to minus infinity. Okay. That negative sign here, I'll just turn around the order in which I'm taking my limits, e to the u du. Okay. That's e to the u going from minus infinity to 0. Okay. Evaluated 0. Now remember, we're taking the limit. When I write this, we're really taking the limit as u approaches minus infinity. We usually don't write e to the minus infinity as such, although I know a lot of you enjoy doing that. Okay, what happens as as u approaches minus infinity? This approaches what? 0. So I end up with what? 1. So my inner integral is 1. So it looks like I squared is the integral from 0 to pi over 2, 1 d theta. And that's going to be what? You can do that in your head. That's pi over 2. That in turn implies, because the value of I is obviously positive, I is the square root of pi over 2. And we've got it, okay? So that freakish transcendental integral we can actually deal with, if we're clever about it, using a double integration in polar coordinates. So there you go.